When you study about split-ring resonators, there will be lots of questions like what is this actually? What is the importance of split-ring resonators in metamaterials? How these structures are providing the negative permeability, and why this structure consists of two rings which is oriented 180 degree? Is only one ring enough to achieve this negative permeability? So there will be lots of questions like this. So in this video, we are going to see answers to this question. Let's see what a split ring resonator is. It consists of two metallic rings, which may be circular or square shape, which is backed by the dielectric substrate, and they have two splits at the opposite ends. These structures, the name split ring resonator was first appeared in the paper by Hardy, WN, in year 1981. But that structure was like metallic ring, that is, it is hollow conducting cylinder with narrow slits. And they proposed these 3D structures for magnetic resonance at low frequencies. You can see the frequency here, which is at very low frequencies. After that, in 1998, 1999, J.B. Pendry proposed our split ring structures as a solution to provide the negative permeability. So this was the first time a structure was proposed for the negative permeability. So by the publication of this paper, the history of metamaterials started. And J.B. Pendry is known as the father of metamaterials. I said split ring resonators are proposed for negative permeability. So first of all, let's see what this permeability means. Permeability is the measure of the magnetization produced in a material in response to an external applied magnetic field. That means it measures how easily a material can be magnetized if we provide an external magnetic field. So the magnetic flux produced inside the material when we apply an external magnetic field is given by this equation. That is, the total flux is equal to mu into h. Mu is the permeability of the material and h is the magnetic field provided. So let's see how this equation works. So first we can assume this is my incident magnetic field. So if I incident a magnetic field on a structure, it has a tendency to provide a magnetic field which may oppose the change in already incidenting magnetic field. So this opposition may be like it may be in the opposite direction or it may be in the same direction. So if the permeability of this structure is greater than zero, these induced magnetic field provided will be very less. That means that the opposition or the enhancement provided will be very less, so that the net flux will be in the same direction as the incident field. So here in the first example, we can see that when I apply an incident magnetic field, it provide an induced magnetic field which is opposing the incident magnetic field. As the magnitude of this induced magnetic field is less, the total flux will be in the same direction as the incident magnetic field. So in the second case also, as the induced magnetic field is in the same direction as the incident magnetic field, the net flux is also in the same direction. But if the permeability is negative, it will be providing an induced flux so that the magnitude of this opposing field is so high in such a way that it will oppose the entire incident magnetic field and the net flux will be in the opposing direction. That means that if the permeability is negative, the material will try to oppose any change in the magnetic field and it will not provide any magnetic field inside the structure. So that is the importance of negative permeability. So the negative permeability did not allow the magnetic field to pass through the structure. So why this negative permeability and permittivity is needed? So the whole idea of the metamaterial structures come into effect because they were trying to develop cloaking structures. That means if we have a structure like this, we have to means produce some materials. So if this is the material, if any wave is incidenting on it, instead of reflecting, refracting or transmitting, all the wave has to bend and go like this. So if the wave bend like this, we won't be getting any idea about any structures inside here. So if we have a structure which can provide negative permeability and negative permittivity, it is easy to provide a cloaking structure. Here we have seen that if we have the structure as negative permeability, it will not allow any magnetic field inside it. So similarly, it will happen for the permittivity. So that is the whole idea of this negative permittivity and negative permeability. So let's see how the split ring resonators are providing the negative permeability. As it is a metamaterial, it is a periodic structure. One of the condition of the metamaterial is it should be sub-wavelength resonance structures. So let's see how the split ring resonators are providing the sub-wavelength resonance. First of all, I am considering a circular loop which is backed by the dielectric. So if a magnetic field is incidenting in this direction, it will provide a circulating current in this loop. So the direction of this current can be implied using the right hand thumb rule. So based on this, this is the direction of the current. So it indicates that when a magnetic field is incident on the loop, it provides some inductance. And as one of our condition is it should be resonance. If it has to be resonance, we should have some capacitance also. To provide the capacitance, I am splitting the ring here. Here you can see that as the current is passing through it, it will provide some capacitive effect as it is like two metals separated by the dielectric. So here we have an inductor and capacitor. So this forms the equivalent circuit of this structure. So here we can see that by using some splits, we can make it as a resonance structure. So this is the resonant frequency of this structure. Here we can see that the resonance frequency is 1 by 2 pi root LC, and the capacitance can be given by epsilon A by D. D is the distance of separation, or this thing. So we can see that when this distance of separation or this split is very less, the capacitance will increase and it will effectively reduce the resonance frequency. So by introducing this split, we are actually reducing the size of the structure. So this split has two impacts. It is providing resonance and it is reducing the size of the structure. Otherwise, we have to provide a half wavelength to get the resonance. So by introducing the split, we can effectively reduce the frequency and the size. So that is the benefit of using the split here. So we have seen that by using a single split ring resonator, we can provide the resonance and the sub wavelength. But in actual cases, we are using two split ring resonator. But it is very important to have two split rings to achieve the negative permeability. So let's see what is the importance of these second split ring in SRR structures. So let's see what is the importance of this second split ring. So in previous slide, we have seen that the resonance frequency is inversely proportional to the capacitance, and as the capacitance increases, the frequency will be decreasing. So if we increase the capacitance further, we can reduce the size of the structure. So it is very easy to design a sub-wavelength structure if we increase the capacitance. So to increase the capacitance, what we have done is we have introduced another split ring like this. So there is a capacitance happening in between these rings because this is the metal, and there is a dielectric in between them. Because of this one, it is also introducing the capacitance. And here we can see that as this area occupied by this structure is very large, this capacitance effect is also large. So in effect, the total capacitance is this gap capacitance and the mutual capacitance. So because of the increase in the total capacitance, the resonance frequency is further reduced. So we are able to achieve the sub-wavelength structure condition here. And one of the question may be like, means why we are introducing the split here, why we cannot rotate it and introduce the split here. Because here you can see that the current flowing through this outer layer is producing the plus and minus electric field indications like this. So for the inner conductor, this is producing the plus and minus electric field indications like this. So these are in opposing directions. So these electric field induced are in opposing direction. So this will reduce the unwanted electric dipole effect. So our structure will be like pure magnetic resonance. We can avoid this electric repulses and we can have a purely magnetic resonance structure. So let's assume if I am rotating this split to this side, then these distributions will be in the same direction, like both will be having plus here and minus here. So it will cause the coupling. So if this coupling occurs, it will impact the magnetic resonance. That's why we are introducing split on the opposing sides so that this electric dipole can be cancelled and this structure can in effect produce the magnetic resonance. That means by introducing the second split ring, we are effectively reducing the size and we are making the structure like a magnetic resonance structure. I hope you get the point. So let's see how this structure is providing the negative permeability in terms of the resonance frequency. So this graph shows the permeability variation with respect to the frequency, and this one is the resonant frequency. Here, this is the resonance frequency, and the effective permeability of the split ring resonator is given as 1 minus f omega square by omega square minus omega 0 square plus I tau omega. Here, this one is the effective permeability, and F is the geometric filling factor. That means how much portion of the unit cell is occupied by the SRR structure. So this will be very high as this SRR will be occupying the most of the area in the unit cell. And omega is the angular frequency, and omega 0 is the resonance frequency, and this gamma is the damping loss due to the resistance and radiation loss. As the SRS structure is a magnetic structure, this loss will be very less. So let's see how this permittivity varies with the frequency, that means the resonance. So below resonance, we can see that this term becomes negative. That means this term will be become 1 plus some value. That means real part of effective permeability becomes greater than 0. So here you can see that as it is 1 plus some terms, you can see that the effective permittivity is increasing from 1 as the resonant frequency is less than, as the frequency is less than the resonant frequency. At the resonance frequency, omega becomes equal to omega 0 and this denominator becomes 0. So because of that, you can see the drastic transition in effective permeability. And because of this term, you can also see some drastic change in the imaginary part of permeability. And above resonance, this omega becomes greater than omega 0 and this term becomes positive, and this is like 1 minus some value, and this will be, as this value f is very high, this becomes greater than 1, then and it will be like 1 minus some greater value, as so it will result in mu effective less than 0. So here you can see that just above resonance, we are getting effective permeability less than 0 here. So this is our area of interest where our SRR structure provides a negative permeability, and this is the relation showing the resonant frequency and the effective permittivity. So now you have seen how these split ring structures are providing the negative permeability. So in most of the papers, you will be seeing these split ring structures backed by these type of strips. So the importance of this strip backing is it will be providing the negative permittivity. So if you have an SRS structure backed by these type of strips, it will provide the negative permittivity and permeability. So this is also proposed by D.R. Smith and J.B. Pendry. So if you want to know more about how this structure is achieving the negative permittivity, means by backing these stripes, how it is achieving the negative permittivity, please comment below. I will be coming up with new video on that. Thank you for listening. If you have any questions, please feel free to comment below. Thank you.